my title is Common Range of Co-analytic Toeplitz operators in the Drury Arveson space. And all of the new stuff I'm going to talk about is joint work with Alexandru Aleman at Lund University, John McCarthy at Washington University in St. Louis, and Stefan Richter at the University of Tennessee in Knoxville. Okay, so let me begin with some fairly classical results in one variable on the unit disk. And I'd like to begin with something that I'm sure many or perhaps all of you in the audience know, which is the Hardy space on the unit disk. So I'll denote the open unit disk by D, and O of D will be the algebra of all holomorphic functions on the disk. Then, as you probably know, there are many ways to define the Hardy space. Here are two. The first one is you can say that the Hardy space consists of all those holomorphic functions whose Taylor coefficients at the origin belong to little L2, so they should be square summable, and this gives you the square of the norm of a function, the Hardy space. And it's a little exercise to show that this is equivalent to saying that these L2 norms over circles centered at the origin should be bounded as the radius of the circle tends to 1. Okay. Now, I'm going to be interested in multiplication operators. So there's a related space, which is H infinity, the algebra of all bounded holomorphic functions on the disk. And one of the reasons why it's important here is that every function m in H infinity induces a bounded linear multiplication operator on H2. So usually when you work with H2, different descriptions might be useful for different purposes. And in this case, if you take the second description, it's fairly obvious that H infinity really gives you multiplication operators on H2. Okay. Now, the title of my talk is includes Toeplitz operators. So let me say a few words about those. So there's even another picture to think about H2, which you can get by taking boundary values. So the point is that these functions are only initially defined on the open disk, but it turns out that it's a theorem of Hartz that for almost every point on the unit circle, the radial limit exists, and it belongs to L2 of the unit circle, and this defines an isometry from H2 into L2. So in other words, we can think of functions in H2 to be at least almost everywhere defined on the unit circle. And so if we make this identification, then you can define Toeplitz operators, which you just get by taking a bounded function phi on the unit circle, so bounded measurable function. And then the Toeplitz operator with symbol phi t phi, you can define by taking, you take a function in H2, you multiply it with phi. So we think of this function f now as being defined on the boundary. Then the result may or may not be in H2, but you can certainly force it back down into H2 by taking the orthogonal projection. Okay, so this is a Toeplitz operator. Now the thing I just defined on the previous slide is a special case of this, because if your function m belonged to H infinity to begin with, then this product will be in H2. There's no need to put the orthogonal projection there. And then you get the usual multiplication operator, which is therefore also called analytic Toeplitz operator, right? Because these are precisely the Toeplitz operators whose symbol is a holomorphic function. It's an easy exercise to show that if you take the Toeplitz operator with symbol m bar, then you get the adjoint of this multiplication operator. So these are called co-analytic Toeplitz operators because they are the ones whose symbol is a co-analytic function. So the complex conjugate is a holomorphic function. So in principle, everything I'm going to talk about, you could understand just in terms of adjoints of multiplication operators, but I wanted to make this remark so that you can see where the terminology comes from. Okay. Well, so why do we bother? Well, these Toeplitz operators, of course, they're extremely well studied. I want to mention one piece of motivation which will become relevant later, which is the von Neumann inequality. So first of all, you can observe that the Toeplitz operator with symbol z is a very familiar operator. It's the unilateral forward shift if you think of H2 in this picture in terms of Taylor coefficients, and therefore Tz star is the unilateral backward shift. And these are universal or model operators in some sense that can be made precise. And in particular, we have this famous inequality of John von Neumann, which says that if you have any linear bounded operator on Hilbert space T that has operator norm at most 1, then you can precisely say how big the norm of P of T, where P is a polynomial, can possibly be. Namely, it's at most the sup norm of the polynomial on the unit disk, or equivalently, this expression is the same as looking at P of Tz of this one special operator. So Tz has norm 1, and this is the maximal a norm it can possibly be for any operator of norm at most 1. In fact, this can be improved quite a bit. Under some mild additional assumption called purity, you can actually realize T as a piece of this operator Tz with multiplicity. This can be made precise in Nages dilation theorem. So I'm not going to explain precisely what this is because it's not really relevant for what I'm going to talk about. But the point here is that these are not just some examples of operators; they actually have a certain universal property. Okay, so the question that motivated our work is a question of Henry Helson's from 1990. And he asked which functions in the Hardy space H2 belong to the range of every non-zero co-analytic Toeplitz operator, or equivalently, which belong to the range of Tm star for every non-zero function M in H infinity. I'll say a bit more about the motivation for this question in a minute, but even just stated like this, if you believe that Toeplitz operators are a natural thing to study, then this seems like a reasonable question to ask. Right. So let's look at this. So first we can do some reductions here. There's something called inner-outer factorization. So here are the operator theorist's definition of inner and outer functions. Function M in H infinity is inner if the multiplication operator is an isometry, and it's outer if the multiplication operator has dense range. These are not the original definitions, but they're equivalent ones, and this is actually a useful way to think about it for this particular problem. But there are function theoretic characterizations of these, right? Okay, so the forefathers of this subject prove this inner-outer factorization, which in particular says that if you take a non-zero function in H infinity, then you can factor it as an inner H infinity function times an outer H infinity function. So this Mi is the inner factor, and the Mo is the outer factor. And in fact, the factorization is unique, or essentially unique, up to scalars of modulus 1. Okay, so what does this say for our problem? Well, if you have an inner function, then Tm is an isometry, therefore Tm star is surjective. So if you do this, then you see that the range of Tm star is just the same as the range of the adjoint of the multiplication operator whose symbol is the outer factor. So the range only depends on the outer factor. The inner factor doesn't give you anything because this Tmi star is surjective. So in other words, if you ask this question of Helson's, then instead of looking at all non-zero H infinity functions, you might as well just look at all outer H infinity functions. And that actually turns out to be very convenient. Okay, so that's the first reduction. So here's the reformulated question of Helson's again. Now, which functions H in the Hardy space belong to the range of every co-analytic Toeplitz operator with outer symbol? Right, it's the same as the original question. Okay, and so that we get a feeling for this question, let's actually look at an example. Okay, so what are good examples of outer functions? Well, maybe the first thing you can think of are functions that are bounded below. But those are not interesting for this question because if M is bounded below, then the multiplication operator is invertible, and therefore Tm star is invertible, and then the range is everything. So that's not very exciting. Okay, so then you should look at functions that are outer, but they're not bounded below in the disk. And so if essentially the easiest example you can think of is you look at M of z is 1 minus z, right? This is an outer function, but it's not bounded below. So let's see what happens for this one. Okay, so what does it mean to belong to the range of T1 minus z star? Well, suppose H is in the range of T1 minus z star, so it's T1 minus z star G for some H2 function G. Well, because Tz star is the backward shift, you can work out what this means on the level of Taylor coefficients. And if you write down what this gives you, it gives you that the nth Taylor coefficient of H is the difference of the nth Taylor coefficient of G and the n plus first Taylor coefficient of G. And these Taylor coefficients, so I'm always denoting the Taylor coefficients of a function with the hat, like in Fourier analysis. Right? So in particular, because these G hat n there and little L2, they converge to 0. So therefore, this sum over the Taylor coefficients of H is a telescoping sum, and it converges. And then in particular, Abel's theorem tells you that the radial limit of this function H at the point 1 has to exist. So this is a non-trivial constraint now, right? Because these H2 functions, I mean, they have radial boundary limits almost everywhere in the circle, but no one says that they have to have a radial boundary limit at the point 1. But if you are in the range of T1 minus Z star, then you have to have a radial boundary limit at the point 1. In fact, there's nothing special about 1. You can replace 1 with zeta for some point zeta on the unit circle. And then you get that this function h, if it belongs to the range of every Tm star, then it has to have radial boundary limits at every point on the unit circle. Okay, and then you can do even better. You can, instead of looking at 1 minus z, you look at 1 minus z squared or cubed, and then you get statements about the derivatives. So if you play this game, then it's not terribly hard to show that if you have a function that belongs to this common range, so this space that Hartz asked about, then all the derivatives of your function have to have radial limits at every point in the unit circle. So it's because of this that we think of this membership in this common range as a smoothness condition, essentially, right? It enforces a certain amount of smoothness on your function, which is considerably stronger than what an arbitrary function in H2 would satisfy. All right. Now, these games, that's all well and good, but we need to have a more systematic approach to this. And this systematic approach also comes from Hartz's work. And his idea is the following. So let's look at the space 1 over mh2. So it's just the space of all ratios of functions of an h2 function divided by n, right? So these outer functions never vanish, so we don't have to worry about dividing by 0. Now, there's sort of a very obvious way to put a norm on this, namely we just carry over the norm from H2. Or in other words, we declare that multiplication by m should be a unitary from 1 over mh2 into H2. Okay. And then there's this really nice result of Hartz's, which says that a function in H2 belongs to the range of Tm star if and only if inner product against this function defines a continuous functional, but not on the Hardy space, I mean, it always does, but on this bigger space, 1 over mh2. Right? So notice the difference here. We take the inner product in the Hardy space, but the continuity should be with respect to this a bigger space, 1 over mh2. Right? So this is a non-trivial constraint. And the proof of this theorem of Hartz's, it's I think it's really wonderful. So I decided to actually show it to you because it can be done in a few lines. So in one word, the one-word summary is it's just the Riesz representation theorem. Okay, but okay. So here's the more detailed explanation. So, well, what does it mean for this functional to be continuous on this space 1 over mh2? Well, 1 over mh2 is a Hilbert space because H2 is. So by Riesz representation, this functional is continuous if and only if it's given by inner product against some function in this space 1 over mh2, right? But now the 1 over mh2 product, inner product. Okay, so let's write this function as g divided by m, where g is an H2 function. And then we have to have this equality here, right? So this is literally just Riesz representation in the Hilbert space 1 over mh2. Right? The continuous functionals on the Hilbert space are the ones that are given by inner product. Okay. Now, on the next step, we have to remember how the inner product in 1 over mh2 was defined, but it's defined so that multiplication with m is a unitary into H2. So let's apply that unitary, we just multiply on both sides by m, and then we get this expression, but now with the H2 inner product, which is the one we sort of understand better. Okay. Now you can do a very simple thing. What you can do is you can take this m here and write it on the right-hand side as a Tm star. And then what you have is just the condition is that for all f in H2, the inner product of f against H should be the same as the inner product of f against Tm star G. Okay, so in other words, H should be Tm star G. And that's it, that's the proof. So what this shows is that the functional is continuous if and only if there exists a G so that H is Tm star G. So if and only if H is in the range of Tm star. So just to recap, the first equivalence was the Riesz representation theorem. The second one was the definition of the inner product in 1 over mh2, and the third one is just cleaning up. So I think this is really a nice example of how abstract functional analysis methods can tell you something about a function theory problem. Okay. Now this can actually be souped up a bit, and then the Smirnov class enters the picture. And again, there are multiple ways to define it, but here's the one that's convenient for now. which is the Smirnov class consists of all ratios of H infinity functions without a denominator. This is an algebra, and it's not obvious, but it follows from inner outer factorization that it doesn't matter so much what the numerators are. So you can also take numerators to be H2 functions, because the point is that every H2 function itself belongs to the Smirnov class. So it's a ratio of two H infinity functions, and the product of two outer functions is outer. So you could also take the numerator to be an H2, and then let's write it in the suggested way on the right-hand side. You take the union over all outer functions of these Hilbert spaces, 1 over mH2. Okay, so this is not just any old union. It's actually what's called an inductive system, which means that if you have any two in this system, then they're contained in a third one. And that's pretty easy, because if you have 1 over m1 H2 and 1 over m2 H2, then it's contained in 1 over m1 times m2 H2. You have to know that, again, that the product of two outer functions is outer. And once you have something like this, an inductive system of Hilbert space, and you have a union, there's a natural topology on it, which is called the locally convex inductive limit topology. So this is the finest locally convex topology on the Smirnov class that makes all these inclusions continuous. Okay. So now I realize this is a dangerous part in the talk, right? You hear locally convex inductive limit topology, then maybe you're tempted to check your email or something. But there's only one thing you need to know about this, which is that the continuous linear functionals in this inductive limit topology are just the ones that are continuous on each of these spaces, 1 over mH2. So in some sense, it's a convenient way of packaging the statement that you should be continuous on each of these spaces, 1 over mH2. Now, if you combine this with the Helson's theorem that I just showed on the previous slide, then you get this corollary, which says that if you have a function in H2, then it belongs to the range of Tm star for every outer H infinity function M, if and only if this inner product functional is continuous on the Smirnov class with respect to this inductive limit topology, right? I mean, continuity on one particular 1 over m H2 space is belonging to the range of that particular guy, and this means you have to be continuous on each 1 over m H2 space. Okay, so you can think of this in two ways. One way is, well, this maybe gives you a handle on how to answer this common range question, because now this says the common range is the dual space of the Smirnov class. Or you can also turn this around and say, well, it gives you additional motivation for studying the common range question in the first place, because the Smirnov class is an object that comes up in the subject quite a bit, and so understanding its dual spaces seems like a reasonable thing to do again. Okay, so that's great, but there's one catch, which is this inductive limit topology is quite difficult to work with. I mean, even if you have a fairly concrete example of a sequence of functions, figuring out if it converges is actually quite tricky, because getting your hands really on open sets in this topology is not so easy. All right, so what can we do about this? Well, there's a different topology on the Smirnov class, which comes from an alternative description of it. So this alternative description works like this. It's a function theoretic one. So you start with a holomorphic function f on the disk, and then you look at these integrals that are written here. So you look at the integral of log 1 plus modulus f, and then you take the sup over r radii, and you define the quote unquote norm of f to be this the supremum over the integrals. This is not a bona fide norm because it's not homogeneous. You cannot pull out scalars, but it defines a metric. So if you declare the distance between f and g to be the norm of f minus g, then this is a metric. So this is often one sees in the subject instead of log 1 plus, one sees log plus, so the maximum of logarithm of the log and 0. But I mean, finiteness of this expression is the same thing in both log plus and log 1 plus, but this turns out to be more useful for defining metrics. Okay, so how can you define the Smirnov class then? Well, it consists of all those holomorphic functions whose norm is finite, and so that the radial dilates of the function converge to f in this metric. So the radial dilate is just f of r z is f of r times z. Okay. If you omit the second condition, if you omit that the radial dilate should converge, then you get what's called the vanilla class. This is a bigger space. And actually, the vanilla class with this metric is actually not so well behaved. It's not a topological vector space. Multiplication is scalar multiplication is not continuous. In fact, it's disconnected. But the Smirnov class with this metric is well behaved. So it is a topological vector space. The metric is complete, and it's fairly tractable. In particular, the dual space of the Smirnov class in this metric topology had already been found by Yanagihara in the 70s, and he gave a very explicit description. So Yanagihara's theorem tells you what the continuous linear functionals in this metric topology are. And well, okay, it's enough to figure out what the functional does to z to the n. So a function is given by some sequence gamma n, and you have to figure out which sequences give you continuous linear functionals. And the condition is a fairly explicit one, namely such a sequence gamma n defines a continuous linear functional if and only if it decays like e to the minus c square root of n for some positive c. So the way that the quantifiers work is that there exists a c so that for all n you have this decay. I mean, just as a sanity check, right? So the Smirnov class is pretty big. It's much bigger than H2. So being a continuous linear functional should be a much stronger condition than being a continuous linear functional on H2. And it is, right? Because the continuous linear functionals on H2 are given by little L2 sequences. And this decay condition is way stronger than being in little L2. Okay, so here's where we stand. So we have two topologies in the Smirnov class. We have the inductive limit topology and we have this metric topology. The inductive limit topology is the one that it sort of was given to us by our problem, by the common range problem. And the metric topology is the one that we can actually work with. Okay, so there's a gap that we have to bridge, or that was already bridged. Namely, this is where John McCarthy enters the picture. And John McCarthy showed that even though these two topologies are different, they're not the same topology, their dual spaces are the same. And so this is something that can happen in topological vector spaces, that you have different topologies, but they give you the same continuous linear functions. So if you know that the dual spaces of these things are the same, and you use Yanagihara's description and Helton's theorem, then you get a complete answer to this common range question. Namely, what you get is that a function in the Hardy space belongs to this common range, so this intersection of range Tm star over all outer M, if and only if its Taylor coefficients decay like e to the minus c square root of n, right? Because those are precisely the ones that give continuous linear functions in the metric topology. By McCarthy's theorem, that's the same as being continuous linear functional in the inductive limit topology, and by Helton's result, this is the same as belonging to the common range. Okay. Again, let's do a sanity check here. So I said at the beginning that membership in this common range should be something like a smoothness condition. So let's see if this is true. Well, if the Taylor coefficients decay like e to the minus c square root of n, then it's very easy to see that all derivatives of your function extend to continuous functions on the closed disk. So this condition certainly implies that your function belongs to C infinity of the closed disk. So it does include these simple games that we were playing earlier. Conversely, perhaps the strongest possible smoothness condition you could demand is that your function extends to a holomorphic function in a disk of radius bigger than 1. And if you're that smooth, then certainly this decay holds, because if you have a holomorphic function in a bigger disk, then the Taylor coefficients have to decay exponentially. And so in particular, they have to decay like this. So this is a condition that's somehow in between being C infinity on a closed disk and having an extension to a holomorphic function on an even larger disk. All right. So this is what was done in the 90s. And so now let me talk about what we did. So what we try to do is to do some of this in several variables. And we were not the first ones to do so. After McCarthy's theorem, people tried to do things like this in the Hardy space on the ball. But I mean, there are results and there are necessary conditions and there's sufficient conditions, but there's actually no complete characterization. All right. We looked at a different space, which afterwards it sort of became clear that for many purposes is actually more useful replacement of the Hardy space on the disk to several variables. and this is the Drury Arveson space that also appeared in my title. So if you know reproducing kernel Hilbert spaces, I can give you a slick one-line definition, which is it's the reproducing kernel Hilbert space on the open unit ball in C to the D, whose reproducing kernel is this function here. So 1/1 minus Z in our product W. So if D is 1, this is the Shagur kernel, you know, for the Hardy space. So if D is 1, this is H2. But if D is bigger than 1, then it's not the same as what's classically known as the Hardy space on the ball. If you don't like reproducing kernel Hilbert spaces, here's an elementary definition. Just like the first definition that I gave for H2, you can characterize it in terms of Taylor coefficients. Holomorphic function on the ball has a Taylor series expansion, so I'm using multi-index notation here. And the condition is that these Taylor coefficients, oops, this should be an alpha, sorry. This should be an alpha. These Taylor coefficients should belong to some weighted little 2 space, and the weights are these multinomial coefficients, so the reciprocals of them. The multinomial coefficients may look strange, but that's precisely what you get when you expand this kernel in a power series. So because you're on the ball, seeing these multinomial coefficients is not so unusual. All right, so the replacement for H infinity is the multiplier algebra, which by definition is the algebra of all holomorphic functions on the ball that leave the space invariant under multiplication. So M times F should be in the Drury Arveson space whenever F was in the Drury Arveson space. And just like before, I'm going to denote these multiplication operators by T, which is supposed to remind you of Toeplitz operators. So T sub M will be the operator F maps to M times F. So our analog of co-analytic Toeplitz operators will be the adjoints of these guys. But it's important to note that even though we think that this is the right replacement, there's no bigger L2 space where these are given by multiplication and then you project down. And this is something that complicates the analysis. Okay, so why do we care? Well, here's a motivation again, which parallels the one I gave you earlier for the Hardy space on the disk. This is the space where you have a replacement of von Neumann's inequality. So a D tuple of operators in the Hilbert space is called a row contraction when you stick them into a row and you think of it as an operator from H to the D to H, then it has norm at most 1. So this row operator, it acts like, like rows act in linear algebra just by matrix vector multiplication. So it takes a column x1 through xd and sends it to the sum of ti xi. So this is one way of defining the operator norm of a tuple of operators in Hilbert space. Okay, and then there is a von Neumann inequality due to Drury, and it was later refined and extended by Müller, Vasilescu, and by Arveson. And it says that if you have a commuting row contraction, so you assume that all these operators pairwise commute, well, then you can plug them into ordinary d-variable polynomials. There's no ambiguity. And then you get a von Neumann inequality like the one I mentioned in the beginning. So if you take a commuting row contraction, plug it into a d-variable polynomial, look at the norm, then the norm is at most the norm of this particular operator tuple tz1 through tzd. So this is a row contraction, and this is the biggest one. In fact, there is a version of this non-dilation theorem in this setting. You can again understand T as a piece of this tuple tz star under some purity assumption and with multiplicity. But yeah, I'm not going to explain the details here. But this is one of the reasons why, for purposes of operator theory, this Drury Arveson space is a very useful replacement of the Hardy space on the disk in several variables. All right. Okay, so what's the common range problem then for the Drury Arveson space? Well, if you have we need an analog of outer functions. So the analog of outer functions are called cyclic, and it's the same definition as the one I gave you earlier, which is that the multiplication operator should have dense range. Okay. So then the question is, which functions in the Drury Arveson space belong to the range of, well, every co-analytic Toeplitz operator, so the range of Tm star for every cyclic multiplier, let's say. Okay. So it looks similar to this original question, but I want to give you a word of warning here, which is that things are different from the one variable setting, and there's sort of two things that are quite different. One of them is that every multiplier is in H infinity, but the inclusion is proper when D is at least 2. And typically the multiplier norm is strictly bigger than the sup norm. So many of the function theory arguments that work in one variable are very difficult to carry over to the Drury Arveson space in general. And also, we don't understand these cyclic multipliers nearly as well as we understand outer functions in the Hartz space. I mean, I didn't give you the function theory description of outer functions, but you can essentially write them all down. And in particular, you can really do computations with them quite well. I mean, there are results about cyclic functions in the Drury Arveson space. So apologies to anyone who's worked on this, but I think it's fair to say that our understanding is not nearly as good as the one of outer functions in the Hartz space. Okay, so this is another thing. The understanding of cyclic functions is not quite as good. Okay, nonetheless, let's see what we can do. So there is an analog of the Smirnov class, which, okay, so the obvious way to define it, if you think that the multiplier algebra is the replacement for H infinity and cyclic is the replacement for outer, then this is what you should do, right? You look at ratios of multipliers with cyclic denominator. You can do a similar thing as in one variable. You have a fair bit of flexibility what you write in the numerator here. You can write Drury Arveson space functions here. There was proved by us a couple of years ago, building on work of Alpay, Bolotnikov, and Kaplan-Loglu. And because of this, you can also write this again as a union of these spaces 1 over mh2d, where you take the union of all cyclic multipliers. Okay, so each of these guys is a Hilbert space in a natural way. This is an inductive system. And so you can put in a locally convex inductive limit topology on it. And the argument for Hartz's theorem that I gave you earlier carries over to the Drury Arveson space almost verbatim, because we didn't actually use any special properties about the Hartz space. I mean, Hartz originally wrote it down a bit differently, but I gave you the version of Hartz's proof that maybe you can believe carries over to the Drury Arveson space. So if you do this, then you get that a function in the Drury Arveson space belongs to the range of Tm star for every cyclic multiplier m, if and only if inner product against this function gives you continuous linear function on the Smirnov class with this inductive limit topology. Okay. Okay, now if you remember in one variable, there was another crucial ingredient, which was, well, there were several crucial ingredients, but one of them was that there was this different description in function theory terms that was much more tractable than the ones with the inductive limit topology. So let's try to do that. So let's define what we call a uniform Smirnov class. So if you have a holomorphic function on the ball, what you can do is you can, for every direction zeta, you can slice the function in direction zeta that gives you one variable function. Then you can say that, well, that should belong to the one variable Smirnov class. You can compute its norm, and then take the supremum over all directions zeta. This is what we do. So it's the supremum over all zeta, supremum over all radii of these familiar expressions log 1 plus modulus of f, but now sliced in the direction zeta. So uniform because it should be uniform in the slice you take, right? Okay, and then we can define the uniform Smirnov class. That should be the space of all those functions where that have finite norm, and the radial dilate should converge to your given function. Okay, so it's just like in one variable, but now you slice in every direction, and everything has to be uniform in all slices. Now this gives, it's not a proper norm, but it gives you a metric, and this uniform Smirnov class is a topological vector space with this metric, and this metric is actually complete. Some things require proof here. I mean, for instance, it does require a bit of an argument to show that scalar multiplication is continuous, but okay, it can be done. Then we have a generalization of Yanagihara's theorem, which is we can describe the dual space of the uniform Smirnov class. And namely, we show that the dual space of the uniform Smirnov class, well, it's given by certain functionals, and turns out to be convenient to write them as inner product against the Drury Arveson space function. And then we get a decay condition on the Taylor coefficients. And so the decay condition is that the Taylor coefficient corresponding to multi-index alpha weighted by some certain weight, omega alpha, should decay like e to the minus c square root of the length of alpha. So again, there exists a c, so that for all alpha this holds. What are these weights? Well, the weights are just the norm of z to the alpha in the Drury Arveson space, which you can write down explicitly. It's one of the square root of this multinomial coefficient. So if D1, this is Yanagihara's theorem, and but now it applies to this uniform Smirnov class. And you may ask, well, why do why does the Drury Arveson space in our product appear here? Well, that's essentially just a convenient way of packaging things again. You can write this out in terms of the Taylor coefficients, and then you don't have any explicit mentioning of the Drury Arveson space in our product, but it's useful to write it like this because it sort of puts the weights automatically where you want them to be. So just a matter of convenience. All right, so here's where we stand, right? So basically we stand where the one variable theory stood before John McCarthy proved this theorem. So we have the we have the inductive limit topology, which is the one that's given to us by our problem. We have this metric topology on the uniform Smirnov class, which is the one we can understand, and we somehow have to bridge the gap. So let's look at this a little bit more carefully. So here are just things I already said. Right, the Drury Arveson space Smirnov class is the space of our ratios of multipliers. Then the uniform Smirnov class is defined in terms of this, integral over slices. But actually, the situation is different from the one variable situation, because in the one variable situation we had two different topologies. Okay, but now we have two different Smirnov classes, right? So that's different, and there's no reason to assume that they are the same, and in fact they're not. So we can show that the inclusion of the Drury Arveson space Smirnov class, so the one defined in terms of ratios of multipliers, so that one is contained in the uniform Smirnov class, but the inclusion is proper as soon as d is greater than or equal to 2. Right? If d is 1, we are in the classical situation, so that's fine, but if d is bigger than 2, then we have a proper inclusion. And in fact, the reverse inclusion fails rather badly. There exist functions in the ball algebra, so they are holomorphic in the open ball, continuous up to the boundary, but you cannot write them as ratios of two multipliers, not even with a non-cyclic denominator. So we don't have the reverse inclusion. So when you look at this, it seems like maybe this uniform Smirnov class will not say all that much about our problem, because okay, not only do we have two different topologies, we actually have two different vector spaces, and it's not so clear what the connection should be. Now, fortunately, it still works out, and so our main result is the following, which essentially, well, now I'm combining basically everything that I already said with a new result, and it says this. So suppose you have a function in the Drury Arveson space, and you look at the associated linear functional just given by the inner product. Then four things are equivalent. The first one is you are a continuous linear functional on the uniform Smirnov class. The second one is your continuous linear functional on the Drury Arveson Smirnov class with this inductive limit topology. Third one is you belong to the range of every co-analytic Toeplitz operator for every cyclic multiplier. So that's the question that I initially raised, right? What is the common range? And the fourth one is something you can actually check explicitly. And namely, we have an explicit decay condition that the Taylor coefficients should, once you weight them appropriately, should decay like e to the minus c square root of the length of your multi-index. So even though these two Smirnov classes are not even the same as vector spaces, it turns out that they actually do have the same dual spaces. They have the same continuous linear functionals, and then it follows that all these sort of various questions have to have the same answer. So I'm not going to go into much detail of the proof here, but let me just tell you how these things are connected. So the equivalence of 1 and 4 is something that I already mentioned. This is essentially this multivariable Yanagihara theorem, right? This is the description of the dual space of the uniform Smirnov class. That's the topology we can understand, and it gives us this decay condition. The connection between 2 and 3, the equivalence between those two is essentially the multivariable Hartz theorem, that this common range, the space that I wanted to understand, is the same as the dual space of the Drury Arveson Smirnov class with respect to this inductive limit topology. Now, the tricky bit is to connect the red equivalences with the blue equivalences, and there's one which is a bit easier, namely going from the red to the blue. This follows essentially from this inclusion of the Drury Arveson space Smirnov class into the uniform Smirnov class. I mean, heuristically, the idea is, okay, if you have a functional that's defined on the big space on the uniform Smirnov class, then it should be defined on the small space, on the Drury Arveson space Smirnov class, and that should be okay. There's actually even a catch there, because this inclusion, while it is an inclusion, it's not continuous. So you have to be a little careful, but it's not too far from being continuous. So this is something that can actually be done. The tricky bit really is to go from the blue stuff to the red stuff. So if you have a functional that's defined on the smaller space, right, on this Drury Arveson Smirnov class with respect to the inductive limit topology, then it should actually, for some reason, also be defined on this big space, and it should also be continuous there. And what we end up proving is actually the implication from 2 to 4. So we don't go to 1, we go to 4. And to do this, the key point is basically that you have to control these cyclic functions. You have to control enough cyclic functions, because, right, if you assume 2, then you're continuous linear functional on this Smirnov class. So you have to somehow say this is a non-trivial constraint, right? And this is only a non-trivial constraint if you have lots of denominators in this Smirnov class, which means if you have enough cyclic functions. In one variable, this part is not bad at all, because it's easy to construct outer functions, right? For every, if you start with some log integrable positive function on the unit circle, you can construct an outer function that has, whose modulus is that, whose boundary function has that modulus. This is something we cannot do in higher variables. So this is where a lot of the work occurs to construct enough of these cyclic functions, in particular to construct things like a least common multiple, which in one variable we can all do with these function theory arguments, and we need to have replacements for this in higher variables. So mentioning this in part because people study cyclic functions in the Drury Arveson space in their own right, and so maybe this could be useful for something else as well. Okay, but once we get enough of these cyclic functions, then can actually show the implication from 2 to 4, and that's the remaining one that closes the loop here. Okay, so all these things are actually equal. So, and of course, in particular, this answers the initial question: what is this common range? Well, the easiest description is it's just like in McCarthy's theorem, given by this decay condition. All right. Here's some open questions to finish up. So I talked about the common range of co-analytic Toeplitz operators with cyclic symbol, right? In one variable, that was the same as having non-zero symbol, because we have inner outer factorization. In higher variables, it's not so clear in the Drury Arveson space. And so I'm going to raise this as a question. What is this common range if you take the intersection of all non-zero multipliers? In particular, is it the same as the intersection of all cyclic multipliers? There is some analog of the inner outer factorization in higher variables, which comes from the non-commutative theory. So it comes from the theory of the full Fock space. It goes back to works of Pescu and Davidson and Pitts. But it seems like this theory isn't that doesn't quite give you this answer here. So if you apply this factorization, you can do it, but it doesn't tell you that these ranges are the same. Okay, so that's still a question. The other question is the one I alluded to earlier, which is what happens actually on the Hardy space on the ball. Right, so there you have co-analytic Toeplitz operators, and the question is, what is the condition there? In particular, is it the same as the one on the Drury Arveson space? We don't know either. We do use that we are on the Drury Arveson space in quite a few places. I mean, if you're in the Drury Arveson space, then the slices belong to the Hardy space. That's something useful. That's no longer true in the Hardy space in the ball. And we also use the fact that, in case you know what this means, that the Drury Arveson space is a complete Pick space. So we use theory of complete Pick spaces here, which is not really available in the Hardy space on the ball. All right. Okay, so this is it. Here's a quick summary. So in one variable, there's this classical theory that tells you that the dual space of the classical Smirnov class is the same as the common range of these co-analytic Toeplitz operators. We did this in the Drury Arveson space. And then you get actually two different Smirnov classes, but even though they are even different as vector spaces, the dual spaces are the same. And if you use this, then you can get a concrete description of the common range of all these co-analytic Toeplitz operators with cyclic symbol in the Drury Arveson space. In terms of decay, just like in John McCarthy's theorem in one variable in the Hardy space. All right.